Hello, my dear students. With our last class, we had ended across with the terms called out as segmentation. Okay, then it can be the terms across where come across with fragmentation as a term, swapping as a term. Okay, address binding. What do you mean by this? Okay, then we had come across with what do you mean by this MMU? Okay, so this is an hardware device. Okay, which helps you maps the virtual address space to the physical address space. Okay, then we had come across with what are the advantages of dynamic linking, swapping as a term. Okay, what do you mean by contiguous allocation? What do you mean by non-contiguous allocation? What do you mean by multiple partition allocation? These all things we have come across. Okay, so today's class we will get across with this one more terminology called it as paging. Okay, what do you mean by paging now? Okay, so paging is nothing but, keep in mind, it is something like wherein the physical address space of a process can be non-contiguous here. Okay, process is allocated physical memory whenever the latter is available. Okay, as soon as the physical memory is available, okay, the process is allocated with that particular working structure there. Okay, so that's why we call that the physical address space of a process can be non-contiguous here. Okay, so what's the use of using paging is it avoids, the very first one is external fragmentation. Okay, in our last class we have come across to know what is external fragmentation there. Then the second one is it avoids problem of varying sized memory chunks there. Okay, so we'll be having, with respect to fragmentation, we have different memory chunks which are being remained across. Okay, so that will be avoided if at all you're using this paging as a concept there. Okay, so what's the use? What's the before we get across with paging as a term, okay, get to know that there are terms which you are using here. Okay, so one is called out as frames, the second one is called out as pages. Okay, one more is page table. Like this will be coming across. Okay, so first of all, get to know what do you mean by uh, frames now. Okay, frames are nothing but you are dividing the physical memory into fixed size block. Okay, and that I call it across with a term called out as frames. Okay, and what do you mean by pages now? Pages is dividing the logical memory into blocks of same size, and that is called out as pages. Always keep in mind, let it be any respective pages or else frames. Okay, they are one and the same with respect to the size. Size of a page is equivalent to the size of a frame. Okay, and usually it is in the multiples of 2. That is, size is usually the power of 2, between 512 bytes and 16 megabytes. Okay, so it keep track of all the free frames there. Okay, to run a program of size n pages, okay, need to find n free frames for that and then load the program. Okay, to do this possible, you require and one more terminology which you are studying here, that's called as page table. Now what is a page table? Page table acts as a translator, okay, between the logical and physical address. Page table is a one which holds, or else which has two contents within it. One is the page number and the second one happens to be the frame number, which page is allocated to with respect to frame there. Okay, backing store likewise split into pages there. Okay, but paging has not overcome entirely the fragmentation as a term there. Okay, it suffers from internal fragmentation. Okay, follow up with that. Okay, so as I said just now with your page table. Okay, so with that respective page table, for every page, always keep in mind there are two contents there. Okay, address is generated by the CPU and is divided into two things there. What are those? One is page number and the second one is page offset. Page number is nothing but which page is going to be assessed there, and keep in mind here the numbering starts from 0, that is page 0, page 1, page 2, so on. Okay, page number is used, as the definition says here, it is used as an index into the page table which contains the base address of each page in the physical memory. Okay, whereas what is this page offset? In other words, you can call it as the size of that particular page. Okay, that happens to be a page offset. It is given by the usage of D as a character, and here it is given by P as a character. Okay, it is combined with base address to define the physical memory address that is sent to the memory unit there. It has two things there, as I said, you page number P, page offset D. Okay, so if at all I have for any given logical address space of 2 raised to m and page size 2 raised to n, okay, your page number holds an address value, or else the size of this is m minus n, whereas page offset size is n. So with respect to defining the same things using your paging hardware, just keep in mind, here comes your CPU. Okay, I have this one just now which I defined. One is page number and the second one is the offset. Okay, and this offset is nothing but you are lying in the logical address space there. Okay, what does this page does now? Page number does, it points to the page table. What's the use of page table? I said to you, page table has two things in it. One is it has page number and the second one is frame number. To which frame is it being allocated? Okay, that frame number is the allocation which goes across onto the physical address size there, that side. Okay, so what do I have there? My header contains two things there. One is frame number and the second way is the same way as the offset one. Okay, one just now I had said priorly, what is the size of your page? The same should be the size of your frame. So that's why always keep in mind the D is pointing to the same D over here. Okay, and the page number is pointing to which frame it will be allocated. Okay, and then there will be a redirection to your physical memory, which is a collection of different frames. Okay, and each frame will be containing of the number of bytes what every page is holding it. Okay, so this is just an paging hardware there. Then followed up with that, this is a small example you can just come across. Okay, what is this? Now in my logical memory I have, now in all I have 4 pages here, page 0, 1, 2 and 3. As I said you will be starting here with 0. Okay, what is my page table having? Page table is having a reference which says me these are my page numbers and these are the frames to which it has been allocated. Okay, what happens in your physical memory now? Okay, redirection. Now like for example page table, okay, it says page number 0 is been allocated in the frame 1. You can just see here it is with, so just see your physical memory is your entire memory space. So here you can just come across it is with 0 to 7 if at all I'm taking an example. Okay, and consider every page is of 2 bytes each. So totally what is the size of your physical memory now? It will be 8 into 2, that is equals to 60. Okay, 16 bytes. Okay, so in those 16 bytes the very first one, the very first frame is allocated to page 0. Okay, page 1 is allocated with the 4 as a frame number. Just consider the 4 as a frame number, page 1. Okay, then page 2 is allocated with the frame number called out as 3. Okay, so that is, yeah, page 2 is allocated with page number 2 is allocated with the frame number 3 here. Okay, just go back here, it is with page 2. Okay, 3 is allocated with 7. 3 is allocated with 7. Okay, and just go across with the similar an example here. You can just consider this is my logical memory. I have 4 pages I had said you. It is page 0, 1, 2 and 3. Okay, what each of these pages is having? These each of the pages is having, like for example, consider these as 1 byte each. So it means that it is an 4 bytes now. Okay, so it is 4 bytes per a page. It is 4 bytes per a page, 4 bytes like this. Okay, and what is your page table holding? It is holding the reference of the frame numbers which every page refers to. Okay, now page 0 is 5. Okay, so here as I said you, it is 4 bytes. Okay, 4 bytes. Then what is your physical memory size now? Okay, physical memory, always keep in mind, do not consider it as only numeric things like 1, 2, 3, 4, something like that. So here when it says page 0 is 5, so which means that how your physical memory spacing, you can just consider the below one. Here n is equals to 2, m is equals to 4. It is a 32 byte memory now. Okay, when I say 32 byte memory, that is your physical address. So I am considering every respective frame is of a size called out as 4 byte. Okay, so ultimately you can just see here I am considering from 0 to 28, which means that it's a 32 byte memory. Okay, page 0 is allocated with 5 here. Okay, so 5 means that 5 into 4. Okay, what will be that? 20. Go with your 20 as an address space, and here you will find your first page, that is ABCD. Okay, similarly go with 1, page number 1, it is with 6. 6 into 4 again 24, so it will be here. Okay, then comes 2, page number 2, it's with 1. 1 into 4 is 4, you can find it here. Okay, that's why I said you always these things are in multiples of 2 only. Okay, not apart from that. Similarly with page 3, it is 2 into 4, that is 8. Okay, these are your free frames which are available. Fine. Okay. Okay, that's an example. Okay, how you are coming across with an, as I said you, it is one of the drawback wherein you have an internal fragmentation there. Okay, now like for example, if I'm considering in terms of bytes, okay, a page size is 2048. Okay, your process size, it's just a small part of a calculation which is given here. Ultimately, to make you to make it feel that each page entry takes memory to track there. Okay, page sizes growing over the time there. Okay, process view and physical memory now are very different. Okay, you can just come across the next one, free frames here. You can just come here. Okay, my free frame list, these are. Okay, and these are my processes. This is with your free, with your before allocation here. Okay, how many pages I have my 4 pages here. Okay, these are my free frame list now. Okay, 14 is free, 13 is free, 18, 20, 15. Need not bother of seriality or something there, sequential there. Okay, they are not sequential, they are given like that only. Okay, what will happen after the allocation? Just go across here. Okay, so it's with a new process now. Page 0, okay, is been allocated with the very first frame, that is 14. Page 1 is allocated with the next frame, that's called out as 13. Okay, page 2 is been allocated with 18. Okay, page 3 is allocated with 20. Okay, this is your new process page table. The same is referred here also. You can just consider these two block diagrams. Okay, so but you will find that there is one more free frame list which has been kept across. That is 15 is remaining back as a free now. Free frame 8. Okay, well, you can have an entry to that. Okay, then comes how do you implement this page table. Okay, so always keep in mind your page table is kept in the main memory and it has two things in it. Okay, one is called it as page table base register. It points to the page table, and one more is page table length register, that is PTLR. Okay, it indicates the size of the page table. Okay, so always keep in mind in this scheme, okay, across it requires two memory accesses there, one for the page table, one for the data. Okay, so the two memory access problem can be solved by use of a special lookout hardware. Okay, that's called out as translation look aside buffers, or else we call it sometimes as associative memory. Okay, so what is this? We'll come across. Okay, so some usually your TLBs are stored in the address space identifiers. In each TLB entry, it uniquely identifies each process to provide address space protection for that particular process. Okay, so always keep in mind whenever you are mapping any logical address, okay, any logical address entry to an physical address, so at that time your page table plays an very important role there. Okay, how and page table allocation is been done. Okay, because it has to lie in the same size where it is lying in a page. Okay, that is that byte only should be extracted from your physical address. To do that only you have this TLBs. Okay, they are usually with the very small sizes which are ranging from 64 to 1024. Okay, on a TLB miss, if consider you have a TLB miss there, value is loaded into the TLB for faster SS next time. Okay, it will be held back in the as I said, TLB stands for your translation look aside buffers. They act as a buffers there. Okay, replacement policies must be considered as usual. Okay, some entries can be wired down for permanent fast SS. Some things you can keep back in the TLBs only, so that you will be assessing it every now and then. Okay, in your page table. Okay, so you can just come across what is this TLB holding, or else what is this associative memory holding. As I said, your every page table is an combination of two things in it. One is page number and the other one is frame number. Okay, so how are you giving it? If P is an associative register, get a frame number out. Okay, otherwise get a frame number from the page table in the memory. Okay, so now our main consideration is here when I have my page number. Okay, now like for example, consider page 0. Okay, it's with an some 2 byte entry there. Okay, so some 2 byte entry wherein you are entering it as 1 2 3 4. Okay, some 2 bytes each you are holding it there. Okay, so wherein we had come across to know that your entry which holds across for every P, okay, it is pointing to your respective TLB now. Okay, so TLB has page number, frame number. If everything is smoothly run, it takes the respective page number, it refers the frame number, TLB hit is right now. Okay, it refers with the frame number, and the offset address remains the same, offset value remains the same as I said you. It points to the physical number. This is one regular case. One, consider it as sorry, one consider that your TLB is a miss now. So at that time, what will happen? This is a page table for that. Okay. In that page table, this is kept for a first traces now. Okay. Directly it points to again with the frame number, again the physical address. Okay. Next time, what will happen? If any such entries come, it does not refer this. It does come back here. Okay. And directly it has been pointed towards the physical. Okay. So now comes and next most asked question or something you can just come across that they'll be asking you for effective SS time to be calculated. Okay, for that effective SS time to be calculated, okay, there's a formula which goes accordingly. EAT stands out for it's equals to H into TLB hit time plus 1 minus H into TLB miss time. Okay, so H stands out for hit ratio. Keep that in mind. Okay, it's usually the probability to find page number in the TLB. If you do not find it, okay, so that's your TLB miss time. If you have found it, that is TLB hit time. Okay, TLB hit time is TLB search time plus memory SS time. Okay, whereas TLB miss time is TLB search time plus twice the memory SS time because it has missed it. Okay, so at that time again, if you want to go across with that, that will be consuming little bit of higher things into it. Okay, now like for example, consider this as an example wherein alpha is nothing but the hit ratio, it is 80%. Okay, whereas you have your you can just come across here associative lookout. Okay, so for your time unit, that's where E that's given as 20 nanoseconds for TLB search. Okay, 100 nanoseconds for your memory SS there. Okay, so memory SS time is it is 100 nanoseconds. Okay, my first time I'm considering effective SS time is hit ratio is 80%. 80 means that it is 0.80 into 100. Okay, plus 1 minus h. 1 minus h is 1 minus 0.80. It's answer for 0.20 into miss time now. What is miss time? You can just come across. What's your search time now? TLB search time. Okay, whatever search time it has taken. Okay, now like for example, if at all it has taken 100 nanoseconds. Okay, for a memory SS. That into 2. That is 200. Okay, so entirely if you go across, you will be coming across with a value called as 120 nanoseconds. Okay, the same thing is being given here also as an example. Okay, so here also you can just consider, and one more example is given, you can just calculate accordingly. Okay, follow up with that, our next consideration is I have to protect the things whatever are there in my memory, what I'm storing in the physical memory there. Okay, memory protection is implemented by associating protection bit with each frame, okay, to indicate if read only or read write SS is allowed. Okay, what you're doing here is valid and invalid bits are attached for every entry in the page table. Okay, that will make it, or else that will make it legally also, and it will tell you directly that whether it's a legal page or else whether it's an whether indicates that the page is not in the process and logical address space there. Okay, or else you can use even your page table length register also. Okay, you can just come across with this example here. Okay, so here onto one side you have your pages here. Okay, in all I have 6 pages with me. I said to you that every page table is a combination of 2 things in it. One is the page number and one more is it will be having usually a frame number there. Okay, so sorry, page number and it will be frame number. Along with this you are adding an flag as an extra entry. Okay, that will tell you whether the bit is valid or else invalid. Okay, you can just come across one example. I'll tell you page 0 is with frame 2. With frame 2 I have page 0 valid. Okay, similarly page 1 with frame number 3 it is valid. Okay, like this go on. Here you will find that page 6 now. Okay, page number 6 it's with 0, okay, as the frame number and it is invalid, which means that there is no such page called out as page number 6. Okay, so I'll be having it with a bit flag called out as invalid. Okay, so what is ultimately the use of that is it will let you know whether the frames are available in your respective page table or okay, that's in your physical memory or not. Okay, followed with that, let's come across with a few more other terms called as shared pages. What do you mean by shared pages? Shared pages are nothing but you all fellows know regarding, you all are aware with the shared memory there, wherein processors are sharing the same respective data segment. Okay, so it is even P1 is accessing the same data, even P2 is accessing the same data, P3 is accessing the same data. Okay, individual operations are different for each of the process. Okay, so in such cases you can opt for share pages so that I can optimize the utilization of CPU. Okay, so it is something like your threads. Okay, multiple threads. Okay, so you can just come across here. Okay, here this is with process P1, this is with process P2, this is with process P3. Okay, what are common here if you come across? Process 1 is also assessing ED1, editor 1, 2 and 3. Okay, P2 is also assessing 1, 2 and 3. Okay, P3 is also assessing 1, 2 and 3, but individual data are different here. Okay, what I can do is I can share in your respective page table. Okay, page 0 of process 1, page 0 of process 2, page 0 of process 3. All the three can be pointing to the same frame called as 3. Okay, second one is page 1. I can make it point to this particular frame called as 4, with process 2 as 4 and with process 3 also 4. All these three will be shared. Okay, whereas only changes will be with the last frame. Data 1 is held in 1, data 2 is held in 7. Your P3 as a process, data 3 is held in 2. The same has been shown here with an example. Okay, this is with your shared pages now. Okay, so let's come across with some differences. Okay, now you will be having a thing in mind that what is so far difference with segmentation and paging. Okay, and one more thing I want to tell you, this paging as a concept you are studying in your next module also, in your module 4, which is all about your virtual memory management there. Okay, so there you will come across again with an extension of this paging. Okay, what are the differences now? Segmentation says that program is divided into variable size segments there, whereas here program are divided into fixed size pages. Okay, the division whatever is been done is been performed by OS there. Okay, here user is responsible for dividing the program into segments. Okay, that's why segmentation is slower than paging, whereas paging is faster than segmentation. Okay, it is invisible to user. Okay, user will he will be totally unaware with the things. Okay, it is visible to user here. Okay, then it eliminates internal fragmentation but suffers from external. Here it suffers from internal fragmentation, whereas there is nothing called out as external fragmentation. Okay, process or user segment number offset is used to calculate the absolute address there, whereas here process or user page number offset are used to calculate the absolute address. Okay, here you have segment number, here you have and page number. Okay, followed with that, this is the next concept, that is structure. What is the structure which is maintained of an page table there? Okay, so for the structure of a page table, okay, you have memory structure, okay, which are for paging that can set and huge using straightforward methods there. Okay, consider a 32-bit logical address space. Okay, so at that time you can say that your page size is of 4 KB. Okay, wherein I will be telling it as it is something called it as 2 raised to 12 number of bytes can be held there. Okay, each page is of 4 there. Okay, so ultimately page table would have 1 million entries there. Okay, so this is a small study regarding every page table there. Okay, this can be handled by hierarchical paging, hashed page tables or inverted page tables. Let us come across one by one. What do you mean by that? Okay, so first one is hierarchical page. Okay, so it is very difficult to allocate contiguous main memory for page table. Okay, one simple solution to such kind of problem is to divide a page table into smaller pieces there. Okay, there are several ways to accomplish it. One way of that is two-level paging algorithm. Okay, or else in other words, you can call it as an hierarchical page table there. Okay, so like for example, every computer system support a large logical address space from 2 raised to 32 to 2 raised to 64. Okay, that is 32-bit or else 64-bit. Okay, yeah, one way to use this two-level paging algorithm is use the page table itself. Okay, so is also used to be paged there. Okay, like for example, you're breaking up the logical address space into multiple page tables. Okay, then that is called out as two-level. We then page the page table. You can just come across with this example there. Okay, this is one process's outer page table. This is another process's page table. Okay, a page table is paging another table. Okay, it has been pointed. Okay, you can just come across this page is been triggered at these two locations. Okay, 100 708, one is 100, one more is 708, like this, 929, 900. Okay, this is a physical memory, this is a page table, this is outer page table. Okay, so two level paging example is nothing but, okay, usually if I say a logical address, okay, on a 32-bit machine, okay, with 1k as your page size, okay, is divided into a page number consisting of 22 bits, okay, and a page offset consisting of 10 bits. The same 32-bit is divided like this. Okay, since the page table is paged, the page number is further divided into 12-bit page number and 10-bit page offset there. Okay, what will be our logical address now? Logical address will be page numbers. Okay, now this is a sharing what is happening across. This is P1 as a page number, this is P2 as a page number, then comes the offset. 12 as a 12 bits is stored exclusively for P1, 10 is stored out for P2, and 10 as the size for both of them. Okay, P1 is indexed into the outer page table, P2 is the displacement within the page of the inner page table. Okay, it is called out as forward mapped page table. Okay, you can just come across here. Logical address is now subjected as P1, P2, and D. P1 is your outer page table. Immediately this will be pointing towards your one more page of the page table, and that will be pointing to the what is it? The size of the respective page. This is address translation scheme, or as you can call it as ATS also. Okay. Next one is 64-bit. The same example for 64-bit as we can. So when it comes across with a 64 division, okay, outer page will be with 42-bit there. Your inner page will be with 10, okay, and your page offset will remain as it is as 12. Okay, so here you'll be coming across with an example, okay, where the second outer table is still 2 raised to 34 bytes in size, okay, and possibly 4 memory access to get to one physical memory location. Okay, so this is one. Okay, there one more is there called it as 3-level scheme also. Okay, 3-level scheme is, this is outer page, this is inner page, and this is offset. Okay, now this same 42 again I am dividing it into one more. Second outer page, inner page, 32, 10, 10, and 5. This is a 3-level paging scheme. Usually it is little hard to use it also. Okay, then comes the second one, that is hashed table there. Okay, what do you mean by hashed page table now? It handles the address space which is larger than 32 bits. Okay, the virtual page number is used as the respective hashed value there. Okay, usually keep in mind every element in the hash table contains 3 fields there. Okay, those are virtual page number, the value of the mapped page frame, and the pointer to the next element there. Okay, so it's like, for example, here you have, this happens to be a virtual page number, then it happens to be the mapped page frame. Okay, and the third one is, it is pointing to the next respective your linked list there. Always keep in mind your hash table is making use of a data structure called as linked list there. Okay, this is your logical address. I apply a hash function to this particular page. Okay, and through that I have a hash table, and that hash table is pointing to my first virtual page number, then it is pointed to the next virtual page number, so on. Okay, and when it comes across with the data what it has to abstract, that is being fetched by the physical memory. Okay, that has been directed to your frame. Okay, and whereas D is fetched from the same page table there. Okay, it comes across here, physical address is being stored across in the physical memory. Okay, so in the same way you have one more, and that's a last one with respect to your inverted page table there. Okay, inverted page tables are something like it, rather than each process having a page table and keeping track of all the possible logical pages there, instead of that the table can be too large to handle that. Okay, what it can do is, each page, okay, it can have an only entry for each page in memory. Okay, each entry is consisted of virtual address of the page stored in that read only location and information about the process that owns that particular page. One entry for each real page of memory. Okay, entry consists of virtual address of the page stored in that real memory location with information about the process that owns that particular page. Okay, it decreases the memory needed to store each page table. Okay, but increases time needed to search the table when a page reference occurs. Use again here also you are using a hash table to limit the search to one or at most a few. Okay, so here you can just come across inverted page table. Okay, it's with CPU. Okay, for every process you have, along with P and D, you have one more header here called as PID. This can be replaced with the page numbers there, P0, P1. Okay, so sorry, not with page numbers, that's with processes. Okay, every process is identified by a PID then. Okay, so which process, okay, for that particular process, which particular page is it going to access? Is it accessing P0? Okay, let me have it in my page table then. Okay, PID with this page table is pointing to this particular frame called as I, and that is redirected to this particular physical number. That is inverted page table. Okay, fine. I hope so everyone has got to know with this section. Okay, in our next respective video lecture, we'll be coming across with our next very module. Okay, that's with your fourth module there. Okay, so that's with virtual memory management. Thank you.